Yeah, on this door we have the access to the batteries, also to the battery switch. All the radiators can be easily accessed without any tooling.
A combustion engine with zero carbon emissions. That sounds like a contradiction, doesn't it? But Liebherr, a company better known for cranes and excavators than revolutionary engines, just unveiled something that could reshape how we think about heavy machinery. They've developed a dual fuel motor that burns two different fuels simultaneously, achieving remarkable efficiency while producing no carbon dioxide. The twist? This isn't meant to replace electric motors everywhere. It's designed to work where batteries simply can't. So what makes this approach so different, and why are we even talking about combustion engines in 2025? The hidden challenge of heavy machinery electrification. When we discuss the energy transition, most conversations focus on passenger cars. Electric vehicles are everywhere now. Charging stations are multiplying, and battery technology keeps improving. But there's a massive blind spot in this narrative. Heavy construction equipment operates in an entirely different reality. A 40-ton excavator or a mining dump truck consumes between 100 and 500 kilowatt hours per day, sometimes more depending on the workload. To put that in perspective, 100 kilowatt hours of energy weighs about 8.5 kilograms when stored as diesel fuel. The same amount of energy in the most advanced lithium battery technology weighs between 660 and 700 kilograms. That's not just a minor inconvenience. For vehicles where every kilogram matters, where payload capacity directly affects profitability, this weight penalty becomes devastating. The machine would be carrying battery instead of doing useful work. And then there's the charging problem. Even with fast charging infrastructure, a 300 kilowatt-hour battery pack needs at least an hour to charge. Without fast charging, you're looking at a full day of downtime. Construction sites would need double or triple the equipment just to maintain the same productivity. Imagine that road construction project on your commute taking not 1 year, but 2 or 3. The economics simply don't work yet. Why construction equipment can't go electric yet? The energy density problem isn't something clever engineering can easily solve. Physics imposes hard limits. Diesel fuel contains about 12 kilowatt hours per kilogram. The best lithium batteries today store roughly 0.2 kilowatt hours per kilogram. That's a 60-to-1 difference. Even if battery technology improves dramatically, closing that gap will take decades. Some researchers propose swappable battery systems, where depleted packs get exchanged for fresh ones, similar to how forklifts operate in warehouses. In theory, this could work. In practice, implementing such systems across thousands of construction sites, each with different equipment and power needs, presents enormous logistical challenges. You'd need standardized battery packs, compatible across different manufacturers and machine types. You'd need transport infrastructure to move these massive batteries around. You'd need charging facilities with enough capacity to replenish dozens of battery packs simultaneously. All of this exists only in research papers and optimistic projections right now. Meanwhile, construction continues. Infrastructure needs building. Mines need operating. We can't simply pause these industries for 20 years while we wait for battery breakthroughs. The equipment operating today will remain in service for another decade or more. This creates an urgent need for solutions that work with current technology, that can integrate into existing workflows, and that deliver environmental benefits without crippling productivity. That's exactly the gap Liebherr identified. Liebherr's dual fuel solution explained. Liebherr's approach sounds almost too simple. Instead of searching for one perfect fuel, they use two fuels that complement each other's weaknesses. The system burns ammonia as the primary fuel, supplemented by either hydrogen or diesel to stabilize combustion. At first glance, this seems needlessly complicated. Why add complexity when simpler solutions might exist? The answer lies in understanding what each fuel brings to the mixture. Ammonia serves as the main energy carrier. It contains no carbon atoms, so burning it produces no carbon dioxide. It's relatively easy to store and transport compared to hydrogen. But ammonia has serious drawbacks as an engine fuel. It ignites only at temperatures around 650 degrees Celsius, much higher than conventional fuels. Worse, it burns about 10 times slower than gasoline or diesel. This slow, unpredictable combustion creates incomplete burning, which produces toxic ammonia emissions and reduces efficiency. That's where the second fuel comes in. By injecting small amounts of hydrogen or diesel alongside the ammonia, Liebherr's engine solves the combustion stability problem. Hydrogen ignites easily and burns extremely fast. When mixed with ammonia, it acts like a chemical catalyst, speeding up and stabilizing the entire combustion process. The result is cleaner, more complete burning with dramatically fewer misfires. The engine itself looks fairly conventional, a 12-cylinder design arranged in 2 banks. Liebherr offers both V configurations and inline arrangements depending on the application. What makes the system special isn't exotic engine architecture. It's the fuel injection technology that allows switching between or combining different fuels. This modular approach means the technology could potentially retrofit existing engines, not just power new ones. How ammonia became a serious fuel contender. Ammonia has been an industrial chemical for over a century, primarily used in fertilizer production. As a fuel, though, it was largely ignored until recently. Why the sudden interest? The ammonia molecule consists of 1 nitrogen atom bonded to 3 hydrogen atoms. You can think of it as a hydrogen carrier, a way to store hydrogen in liquid form without the extreme pressures hydrogen requires. Producing ammonia starts with hydrogen. Using renewable electricity, you can split water into hydrogen and oxygen through electrolysis. That hydrogen then combines with nitrogen extracted from the air through a process called the Haber-Bosch synthesis. The energy efficiency of this conversion is surprisingly decent. While you lose some energy in the conversion process, using ammonia as fuel is 2 to 3 times more efficient than producing synthetic diesel or gasoline from renewable electricity. The real advantage shows up in storage and transport. Hydrogen becomes liquid only at -253 degrees Celsius, or when compressed to 700 bar. Both options require expensive, specialized equipment. Ammonia liquefies at just 10 bar of pressure, roughly what you'd encounter inflating a bicycle tire. This means existing infrastructure, tanker ships, pipelines, storage tanks, can handle ammonia with minimal modifications. The chemical industry already moves millions of tons of ammonia globally every year. That infrastructure could be repurposed for fuel distribution. But ammonia isn't without problems, and they're serious ones. The substance is toxic and corrosive. It has a pungent smell that's unmistakable, even in tiny concentrations. Handling it requires training and proper safety equipment. Still, industries have managed these risks for decades. The bigger challenge is making it burn properly in engines. The hydrogen-ammonia partnership. Pure ammonia engines have been tested for years with disappointing results. The slow combustion speed creates a cascade of problems. Power output suffers because the fuel doesn't release its energy quickly enough during the engine stroke. Efficiency drops because combustion continues even after the piston starts moving downward, wasting energy as heat instead of mechanical work. And incomplete combustion leaves unburned ammonia in the exhaust, which is both toxic and wasteful. Mixing in hydrogen changes everything. Hydrogen has the fastest flame speed of any practical fuel. When ignited, the combustion front races through the fuel mixture. In a dual fuel system, hydrogen ignites first, creating a rapidly expanding flame front that then ignites the surrounding ammonia. This essentially pulls the ammonia into faster, more complete combustion. The hydrogen acts as an ignition enhancer and combustion accelerator. The ratio matters. Too little hydrogen, and you don't get enough improvement in combustion stability. Too much hydrogen, and you lose the main advantage of using ammonia, its easier storage and handling. Liebherr's research focused on finding the optimal balance. Their injection system can adjust the mixture in real time based on engine load, operating conditions, and performance requirements. Interestingly, the system also works with diesel as the secondary fuel instead of hydrogen. This offers flexibility during the transition period. Construction companies could run their equipment on ammonia diesel while hydrogen infrastructure develops, then switch to pure ammonia hydrogen once hydrogen becomes more readily available. The engine doesn't care much. The injection system handles both scenarios. This flexibility might be the technology's most important feature. It doesn't demand perfect conditions or complete infrastructure before deployment. Technical implementation and modular injection systems. The breakthrough that makes Liebherr's dual-fuel engine practical came in February with their announcement of a modular injection system. Traditional fuel injectors are designed for specific fuels. Gasoline injectors differ from diesel injectors, which differ from natural gas injectors. Each fuel has different properties, pressure requirements, and combustion characteristics. Designing an injector that handles multiple fuel types, especially both liquids and gases, represented a significant engineering challenge. Liebherr's solution uses what they call a modular approach. The injection system can accommodate gaseous fuels like hydrogen and methane, as well as liquid fuels including ammonia, methanol, ethanol, and conventional diesel. The system likely uses separate injection ports or sophisticated valve mechanisms that switch between fuel types. The exact technical details remain proprietary, but the result is clear. One engine platform can now run on multiple fuel combinations without major hardware changes. This matters enormously for industrial applications. Equipment operators can adapt to whatever fuels become available in their region. A mining operation in Chile might use ammonia produced from solar-powered hydrogen. A construction company in Germany might mix in locally produced biogas. A port facility might run on ammonia imported by ship. The same basic engine handles all these scenarios. Beyond the injection hardware, the engine management system needs sophisticated control algorithms. Combustion timing, injection quantities, air-fuel ratios, all these parameters change depending on which fuels you're burning and in what proportions. The engine computer continuously monitors combustion quality through sensors and adjusts the fuel mixture to maintain optimal performance while minimizing emissions. The NOx problem and environmental trade-offs. Here's where the story gets complicated. Burning ammonia solves the carbon dioxide problem but creates a different issue. Nitrogen oxides, collectively called NOx, form whenever nitrogen-containing compounds burn in the presence of oxygen at high temperatures. Ammonia is essentially concentrated nitrogen, so NOx formation is inevitable. These compounds cause serious health problems, particularly respiratory issues. They also contribute to smog formation and acid rain. Trading carbon dioxide for nitrogen oxides isn't an acceptable solution. Fortunately, technology to remove NOx from exhaust gases already exists. Selective catalytic reduction systems, which use chemicals to convert nitrogen oxides back into harmless nitrogen and water, are standard equipment on modern diesel engines. Ammonia-based engines would need even more aggressive NOx treatment, but the technology is proven. The challenge is making sure these systems work reliably under all operating conditions. There's also the matter of optimizing the combustion process itself to minimize NOx formation. This involves precisely controlling combustion temperatures, timing the fuel injection carefully, and ensuring thorough mixing of fuel and air. Each percentage point reduction in NOx formation at the source means less work for the exhaust treatment system and better overall efficiency. The industry needs to be realistic here. Early versions of this technology will likely produce higher NOx emissions than desired, but that's how all new engine technologies develop. The first diesel engines were dirty and inefficient. Decades of refinement made them viable. Ammonia engines are at the beginning of that development curve, where this technology actually makes sense. Not every application needs or benefits from dual-fuel ammonia engines. Personal vehicles? Electric motors have already won that battle for most use cases. Battery-powered cars work brilliantly for daily commuting, and the charging infrastructure continues improving. Long-haul trucking looked like a strong candidate for alternative fuels until recently. Then, Chinese battery manufacturer CATL announced truck batteries with vastly improved energy density and charging speeds. 15 minutes to 70% charge with enough capacity for extended range suddenly makes electric trucks economically competitive with diesel. That market might already be lost to combustion engines, regardless of fuel type. Heavy construction equipment, though, remains firmly in combustion territory. The weight constraints are too severe, the power demands too high, and the operating patterns too unpredictable for current battery technology. Mining trucks that haul hundreds of tons up steep grades, excavators that dig continuously for 12-hour shifts, mobile cranes that need maximum lifting capacity, these applications genuinely need the energy density that chemical fuels provide. Marine shipping represents another obvious application. Large ships already burn heavy fuel oil, one of the dirtiest fuels available. They consume enormous quantities crossing oceans. Battery-powered cargo ships remain impractical for anything beyond short coastal routes. Ammonia fuel offers a realistic path to decarbonizing this massive industry. Several shipping companies are already testing ammonia-powered vessels. Aviation might also benefit, though the engineering challenges are even more demanding. Aircraft need maximum energy density and absolutely reliable engines. Ammonia's combustion characteristics make it tricky for aviation use, but research continues. The shrinking domain of combustion engines. 10 years ago, internal combustion engines dominated nearly every form of transportation. Today, that domain is contracting rapidly. Battery electric vehicles have captured the passenger car market in many countries. Electric motorcycles and scooters are everywhere in Asian cities. Electric trains have been standard for decades. Even aircraft are beginning to go electric for short regional routes. Each improvement in battery technology claims another piece of territory that combustion engines once held exclusively. The pace of change keeps accelerating. When CATL announced their new truck batteries, conventional wisdom about heavy-duty transport shifted overnight. Technologies that seemed years away from practicality suddenly became commercially available. This creates tremendous uncertainty for companies developing alternative fuel engines. The market they're designing for might not exist by the time their products mature. Liebherr's modular approach makes sense in this context. By creating an engine platform that can burn multiple fuels, they've built in flexibility against an unpredictable future. If hydrogen infrastructure develops faster than expected, the engines can use more hydrogen. If ammonia proves too challenging, they can fall back to renewable diesel blends. If batteries improve enough to make even heavy equipment electric, well, at least they tried. One thing seems certain. The era of fossil fuel combustion engines is ending. What replaces them in each specific application remains an open question. For some uses, it'll be batteries. For others, hydrogen fuel cells. And for a subset of heavy-duty applications where energy density matters most, dual-fuel ammonia engines might find their niche. The next decade will determine which technologies win in which markets. Looking at Liebherr's dual-fuel engine, it's tempting to see it as either the future of combustion or a desperate attempt to preserve the past. The truth is probably somewhere between. This technology won't replace electric motors. It will serve alongside them, filling specific roles where batteries remain impractical. As construction equipment moves away from diesel, as ships seek cleaner fuels, as industries worldwide scramble to reduce carbon emissions, solutions like this dual-fuel approach provide bridges to a cleaner future. Not perfect solutions, bridges. And sometimes a bridge is exactly what you need.